Okay, we start today's lecture. The topic is on the bull plots. The content is on this lecture handout. You should be able to get it from Moodle. Okay, everybody got this handout? Any questions? Okay, first of all, an announcement. Right, I've put up an erratum, a correction on Moodles about the comparison between the break frequencies that we went through it in the last lecture. Right. In Moodle there's a directory called additional reading, and then I have already put up another PDF file. Okay, let us continue on the bull plots. So if we given a system to be controlled, and in particular, the input is a sine wave. A sine wave can have a different amplitude and or frequency. And then we also have a specification. Also have the system specification. The system specification is very important for any control system. For example, we may require the steady state error. It is smaller than some percentage of input. And then we can also specify that the system should be stable. And then we can also specify that the rise time or the settling time is smaller than so many seconds. Okay, we can have a lot of specification that we can put into the system. And then in order to satisfy all the specifications, we need a proper design. Need a proper proper design the controller. So far, agree with that the scenario that we are facing in a control system. Then in order to carry out the design, we need to know the system, right, before design. We need to know the system. And then how we can know the system? For example, we input sine wave at a frequency omega 1, right? And then measure output omega 1, measure output. And then we input frequency omega 2, and then we also measure output omega 3, etc., etc. So in measuring all the frequencies, different frequency values, we know what the system is behaving. So the next question, right, or the next question. The next question is that, are measurements correct? So in order to know if the measurements are correct, then we need some references. And then the references come from modeling. From the modeling, for example, from the physics law, and then we have a differential equations. And then we can have the Laplace transform. So the importance is that we need to have some reference before. We need to have the reference before making measurements. Okay. So the bold pot, okay, it is one of the reference. In graphical form. And then it shows the magnitude or the angle of the system with respect to frequency. Then we look at how to obtain the bold pot. From here, we start looking at a general system. Okay. We consider a general system. G of in the Laplace domain, G of S. So this system, right, will be configured in a feedback system. So it means that we can have the G here, and then this is output, and then we have the sensor, and then we can have another controller, and then the error summation term, and then there's another controller. So temporarily, we call it H1, H2, H3, and this is the input. So this is the system that we are considering. So we can see that G itself, GH2 itself, multiply together, and then GH2H3, and then feedback combination, and input scaling H1, right? All affect the output. And then, of course, most importantly is the G. So usually G is the physical system. And then H3 is the sensor for feedback. And then we call H2 is the controller. And then H1 is also the controller. And one very important thing is that H1, 2, and 3, this can be electrical circuits, that is, it can be a computer program. So it means that the system output can be modified with a proper setting of H1, H2, and H3. And the proper setting, we mean that it is the design of controller. Okay, so far any question? Any question? So far, okay. So we look at a general case, right? So the GS equals A S plus A S plus B S squared plus B S plus C K D. Or in another way, we have the S plus A S squared plus B S plus C. So they are the general cases. So first of all, we can separate the transfer function. G of S into components. So we have the GS equals K times S times S plus D, and then times S plus A times S squared plus B S plus C divided over 1. So we divide the transfer function into components because they will be represented as complex numbers. Then this transfer function is a complex number. So in calculations concerned with the complex numbers, we know that, right? The complex number has two components, the magnitude, and then also have the phase angle. And we also notice that for multiplication, the magnitude of the result comes from the magnitude of different components. They multiply together. And then for the angle, it is angle magnitude 1 to angle 1 plus angle 2. And then for division, the magnitude of a complex number division. So we have magnitude 1 divided by magnitude 2. And then the angle, it is angle 1 subtract angle 2. And we also looked at if we're taking the logarithm. Okay. In logarithm scales. The multiplication becomes our addition, and then subtraction become, and then division is in fact the subtraction. So because of this change, right, the multiplication becomes the addition of angle, and the division becomes the subtraction of angle. And then we, in the logarithm scale, multiplication becomes addition, and division becomes subtraction. And that makes the calculation easier. That all them make the calculation easier. Okay. Then we look at different components. Okay. So if for the gain term, that is the k. So we know that the magnitude is 20 log base 10 of k, and then the angle equals arctangent so it is a constant irrespective of the frequency omega. So the angle is 0 degree. It's also irrespective of the frequency. So now we can plot the magnitude somewhere at this point. Okay, so this is 20 log 10 of k. And then for some angle. So this point is 0 degree. Both the magnitude and the phase angle are constant irrespective of the frequency. And then for the integral or differential, so for the integral it is s, and then for differential it is 1 over s. So this is from it is from Laplace transform. The integral or the differential theorem So now we put S equals J omega. then the magnitude is 0 plus omega squared. Okay. So we imaginary that we have a real part, and then this is the imaginary part. And then the angle is the opposite then over the imaginary over the real part. So it is 19 degrees. Okay. So we have the real part, the imaginary part, and then this is omega somewhere, but the real part is always 0. So we have this 19 degrees. So for the magnitude, here omega, magnitude is equals to omega. When omega is 0, then the magnitude is 0. And then it is omega equals 1 here. So we have 20 log 10, 1. So it is our 0.0 decibel. So as omega increases, so we also have the magnitude increase. Then and for the phase angle, the angle is always here is 90 degrees. So for the integral term for 1 over s, so it is the inversion of s. So from the properties of complex number, the magnitude inversion, so it becomes a negative logarithm. So the angle inversion, so it also becomes a negative angle. Okay. So the plot is that for the magnitude, so we have the 0 decibel here, and then it's omega equals 1, and then it goes down. And then for the angle, So it is minus 90 degrees. And then for other terms, for the first one, S plus the 1 over S plus A term. Then we have S plus D implies that it is D plus J omega. And then the magnitude, it is D squared plus omega square root. And then the angle, so it is arctangent the imaginary part divided by the real part. For these cases, right? So for these cases, so it is not purely imaginary. So we define a particular case. We call again break frequency. That is when omega equals D. So this case is the real part equals the imaginary part. So at this frequency, omega equals D, the magnitude is this one, and then the angle. So it is D squared plus D squared, and then equals D and then root 2. And then the angle is so it is 45 degrees at this particular frequency. So for the magnitude, here omega equals D, this point, and then the magnitude is 20 log 10 D root 2. Depends on the value of D. Then we have different values. And then for the angle at this particular frequency again, so it is 45 degrees. Okay, any questions so far? So for this case, S plus D for this case. So if now change the D to 0.1 D, change omega to the 0.1 D, then the magnitude becomes D squared plus 0.1 d square. So it is d square plus 0.01 d square square root. Then it is also equal to d and then 1.01. Yes. So it is approximately equal to d itself. And then again, if omega goes to very small, 1/10 of d, then the magnitude is d squared plus 0.01 d. So it is d. So again, it is approximately equal to d. So for higher frequencies, right, if omega goes to 10 d, then the magnitude is so it's d squared plus 100. So it is approximately 10 d. So if omega goes to 100, then the magnitude is so 100. So it's 1, 2, 3. So it is approximately 100 d. So if we then we take the logarithms. So we have 20 log 10 d root 2 and omega equals d. Okay, and then 20 log 10. So it is d at omega 0.1. Then 20 log 10. It also adds omega equals this one as 0.1. So it is 10 d. And then it is 100. So for this part, okay, it is a multiplication between 10 and d. So it turns out to be 20 log 10, 10 plus 20 log 10 d. And then this one is 20 log 10 100 plus 20 log 10 d. Because we are taking the logarithms. So log 10 of 10 equals 1. Then, and then log 10 100 equals 2. then the magnitude ratio and omega equals 10d and then 100d. So it becomes 20 times 2 so then we minus 20 times 1 plus so it is 40 minus 20 okay it's 20 8 with respect to 10d. So the frequency ratio of 100d to 10d, we call it a decade. So it is 10 times. So we define so the increase in magnitude is 20 decibel per decade. So, okay, any questions so far? Yeah. It contains two parts. This part is almost no change. See that? Right. So this part, it is increasing. So for the d plus j omega for this term, the magnitude is omega somewhere at d, and then here is 0.1 d, here is 0.01 d. So those are these two levels are not changing, and then here with 10d, and then another 100d. And then the difference here is 20 decibel. And then here we see that the frequency ratio, so it is also 10 times. So we have a straight line extension, And then also again, from 0.1d to d, we can also have a straight line approximation. Okay, but recall that the magnitude is 20 log 10 d root 2 at omega equals d. But at this point, for the 0.1 omega, it is 20 log 10 d. So the difference between log 10 d root 2 in 20 log 10 d. The transmit rate is 20 log 10 d plus 20 log 10 root 2 minus 20 log 10. So it is 20 log 10 root 2. So it is 3 decibel. So here we have this point. This point is 3 above this value. And because of this difference here, okay, so we have this straight line. We also call it a straight line approximation. Okay, everybody get the idea? And then it is very important to note that based on the value of d, value of the plot shifts horizontally. Across omega. Okay. And then the plot shifts vertically according to 20 log 10 d square root 2. Okay, it all depends on the numerical values. The numerical value of d, if we have a different d, if it is 1, for example, and then in another case d is 10, then the plot will shift to the right to the higher omega. And then it also depends on the 20 log to the base 10 of d. The plot also shifts up and down depending on the value of D. So for the other case, for 1 s plus a, so is it treated as inversion of s plus d with a equals d. Okay, it's just that simple. And then for the magnitude, so we have a upon 1 of a, and then 0.01 of a. There's no change. And then for 10a, 100a, then we have the inversion from positive to negative, and then the difference also is still here. It is 20 decibel per decade. So if we have this case s plus d, s plus a, right? In this case, if they are not equal, then what happens then? So we know that it we have d 0.1 of d, 0.01 of d, and then 10 d, then 100 d. So if we have the okay, this curve is for s plus d. And then we have another term, s plus a, if our a is here. And then if our 0.1 of a here is 0.01 of a, then here is 10a, here is 100a. So there is no change at 0.1 and 0.01. And then at 10 we have this, and then 100 we have this. So we observe that the s plus d, s plus a, we can put it this way. It is multiplied with s plus a. So in the logarithm scale, okay, the multiplication becomes addition. Then we do it carefully. So it is 0.01 d, 0.1 d, and then d, 10 d, 100 d. And then we also have then here is a is 10a, 100a. So up to this point, from 0.1 from 0.01 d up to d, right? It is all at the same line. So up to d. So up to d here. There's no change. And then at this portion between D and A, so it increases. So between D and A, it increases. But after A, so this increases, but at the same time, it also decreases. So here, it is the same. So we see the increase in S plus D, okay, cancelled by so it is very important to notice that in the logarithmic scale, the multiplication becomes an addition. So it is very easy for us, right, to construct the Bow plot that characterizes the system. Okay. And then if we can accept the approximate error, we can do it very simply by hand calculation. Okay, is that okay so far? Okay, if there's no question, then we'll take a break and then we start the interactive tutorial.
That's why no one knew what they were.
Yeah, they were like
something about.
confusing, right?
No, it's just they're not going to lectures. I asked my class, and like, out of the 10 of them, there's not a single one. Like, I was like, honestly, like, I need to know. Have you guys been to the lecture? And nobody put their hands up. I'm like, no.
So I want me to do the lecture for them next Tuesday.
Well, that's the thing. Like, I just brought it up, and I was like, look, basically, like, first order this way, second order this way. You got to do it yourselves. But I point them. Have you seen that? What is it? Brian. It's Brian Nicholas or something. YouTube lecturer guy with the like black background and coloured writing. YouTube lecturer. I just point them to that. I'm like, if you don't know what's going on, watch these guys' lectures, and they explain everything.
Yeah, I told him to visit that SWOT course.
Yeah.
Yeah, asymptotic.
Yeah.
Because you can do the entire science.
Yeah, exactly.
I remember last year that was alright.
Yeah. Showed them how to use it.
I forgot that.
Yeah, that's why I didn't have much time. I showed them how to use
What's
it
the
in the
name?
tutorial.
What's the
You
name?
just Google it.
The name? Both not?
Yeah, I just Googled Boatplot and it's
There's so much stuff out there. Like all the American unis
not
have.
too hard of a concept, it's just you have to sort of know what you're doing.
Yeah, you can't
And once
just
you know
look
what you're
at
doing, it's like the easiest thing.
Oh yeah, and it's the same every time. Like it's like 3 or 4 equations. That's it.
Kids in lecture are like, can you do lecture? I'm like, you guys should chip in $5 each.
Yeah, I know. I'm not going to sit there teaching. I was like, you better make sure you know what to do.
I don't know how much to pay.
Yeah. And so did you end up starting? You didn't start any bird plots this week?
I did one of them.
Yeah. I didn't. Did you start on the first one? Yeah. I looked at it. I was like, yeah. I went straight to the third one. That first one was way too brutal. Like zeros, poles, and complex
They don't
stuff.
do the complex positive.
Yeah, exactly.
啊，它第二篇是什么？这第二篇一个 A 一个什么？是 void jobs, I think it belongs to the right. So maybe hedge point. What do you think? Based on the, you can double check with the top. Yeah, because there's no definition. But based on this point, the name is there. Oh, okay, it's Zara. Zara, okay. It should be near the TP. Okay.
Nowadays, till nowadays, you just need six levels. Then you sort of control it.
Okay.
Okay, for example, some definition 10 to 90 or another different definition. And then it's place. It's place. Something like with respect to the damping, something like that. We can have you can find out almost anything.
Yes, I was looking. Everything is around 50. But it seems, you see, sometimes there is a break. Why this one got like, where is the week 8 or week 9 or something?
Okay, I put it into
Right?
same thing.
Okay, it's the same. Because they are stupid.
Yes.
Interesting. So every part is around 15, but no students.
The other tutors told me that you are very good in control engineering
In what?
in this subject.
Oh, this one. I was like, just need to run the tutorials well. That's
So you like mathematics a lot.
yeah. I like it. I like maths a bit more, but we don't do much mathematics in mechanical engineering. So yeah, I got hired to do maths before, but that didn't turn out very well. For everything in this part of the course should be okay. Mathematically, it's not too hard.
It depends how do you believe that I want to go into the topic.
Yeah, yeah.
Yes, this is the real part is the same. So the speed is the same. Possibility of becoming stable is also the same. But it has a better less
Is that a question? That is not a question.
Hello, Doctor.
we got a question. Because just now it's a circle. This one it is a straight line. It's a straight line. So the real part will always be the same.
I did last week Monday and this week Monday and Tuesday.
So because the other one
1.5
has
hours
a
on Monday
solution,
and 1.5
but they have the same real part.
Tuesday.
Real part.
Yeah, I had one on Thursday, but it's cancelled.
Oh yeah, so yeah, because of that I have to do 9 to 10 next Tuesday.
Oh, Tuesday.
Yeah, yeah. Gonna run another one next Tuesday.
And there's one on Thursday as well. I have to do one on
Oh, next week Thursday.
Thursday.
Yeah. I didn't want to come in at 9 a.m. but I had to. Otherwise people wouldn't get the things done. The steady state error is 1 on 1 plus k.
Yes.
Because that's what I told everyone, but I didn't know if that was the correct answer.
I need to look up. I think it is 1 upon 1 plus GH. So.
Magnitude of G is 1.
No, H is 1, right? The feedback is 1.
Yeah. Okay, I don't remember. I can figure it out.
Yeah.
I was awake for like 30 hours straight doing the assignment.
For
Didn't
which
even
course?
prepare for my tutorials today because I didn't have time.
So in the past, you're doing the passive ones as well, right?
Yeah.
So that. Next week you have to do quadratic ones.
Yeah, we were supposed to do red plot today, but then they just told me that they started red plots today. So I was like, that's why no one used it. But then, yeah. I'll see next Tuesday. I might do something different. I might just tell them how to do it. I won't even go through the questions.
Yeah, because those tutorial problems already have solutions.
I mean, if they don't come to lecture, then I sort of push them in the correct direction. But an hour's not enough for like telling them how to do types of questions. I've got a tutorial to run after this as well, and I haven't prepared for that either, so gonna have to make all things.
You can give the students 5 minutes. Just take 5 minutes to solve the problem, and then
Yeah, and then I do it.
in the 5 minutes, that happened to me in one of my other class, thermodynamics. What happened was I read up, I prepared it for a bit. You're doing that course?
Oh no, I'm tutoring solid next year.
For thermo, what had happened was I read up the wrong week, so I went. I went there and the student was like, oh, we have to do tutorial 9. Oh shit, I haven't tutorial 8. But there was another tutor,
Oh, right.
so thankfully the first 10-15 minutes he was.
Thermodynamics, I remember that you weren't supposed to do questions. Tutorials.
No, it's changed now.
Maybe I should
It's like a passive tutorial now.
Oh, that's much easier. I remember when I did thermo, it was like their lecture notes like on Moodle there was literally nothing on Moodle except the questions they had in Moodle and the course outline. That was it. That was all that I had for the course.
But you have problem solving interaction sessions with the tutor?
No, I never went. I never went lectures either. I just did quiz 1, quiz 2 in the exam. But, you know, everything was textbook questions, so it's not like that.
The transfer function, the block diagram, the second half. I think some people messed it up quite bad, but there were a lot of students who got it all right. Do you know roughly what the average was for that? No, I didn't evaluate it because I didn't enter the marks in a spreadsheet, so I did them. So, yeah.
Yeah, because it looked like some of the results were in before for that. Sorry, you got the original. You got the top guy.
Then it was
Just
easy.
messed up. Sorry, I was
The
like,
unit step and
because the game was 8 questions.
the last one,
So I
actually
thought it was
very
over 1 week, so I had to do 4
that
today.
right.
Turns out it's over 2 weeks.
Time constant is smaller.
I got enough time to
3T1, e raised to 3T, smaller time also.
What a good day it is today.
I think the average would be decent.
Everyone got scared by the first one. Because that
So you can't understand by. But what do you mean by this one? You mean it's
I should buy this. Such a fancy shirt for Brett for like for work. It's got like just with what you were saying before.
is that the
So it comes to this for this case, because it's a unity negative feedback, that means that I get other
Yeah, this guy's ages.
because so that just means that
which one?
the error carry obviously is
Actually, even last year,
which is equal to the difference.
different now.
Yeah.
Passive plus
But one thing you have to realize is that there's only one